Hi everyone, let's run through some week 5, which is our second week of probability. This week we're doing experimental and theoretical probability. Not a big week, I don't think. So, firstly, what's the concept of probability? Well, it's, as it says, it's a means of describing the chance or likelihood of a particular outcome occurring. Again, we might use the term experiment when we're doing an experiment, which again doesn't mean lab coats and that. It means I could be just rolling a die. Single of dice, rolling a die, I could be tossing a coin. That's an experiment, okay? And the scale of probability is from 0 to 1. It doesn't matter whether you refer to as a decimal or a fraction or percentage. Like here, certain says an event always happens. Well, certain is up here at a probability of 1. Or you can call it 100% if you want. The same way that an impossible event, well, that's a probability of 0%, same thing. And right in the middle, an even chance, well, that's a probability of a half. Call it 0.5 if you want, because that's the same thing. Call it 50% if you want. That's the same thing. So it doesn't matter whether you express as a percent, decimal, or a fraction. There's that probability. And they're the definite ones, 1, a half, and 0. Other ones, very likely, well, they don't have set number probabilities. We just know the concept that very likely probably means, 90%. It's not a purely mathematical definition, it's just regions of likelihood. Now, as I said there, experiment, okay, got the same thing there. Experiment is just something that we're doing, that has certain different outcomes that might have different probabilities of occurring. And the term outcome just means the result, like tossing a coin. I've only got 2 outcomes, a head or a tail. We could describe it like last week and say, well, what's the set of outcomes of tossing a coin? Well, here's a set of outcomes. Curly, again, terrible. Curly bracket, head, comma, tail. Alright, there's only 2 elements in the set of potential outcomes. At some stage we're going to actually refer to that as a sample space as well, a list of all the outcomes. But okay, we're not there yet. And expectation. Well, the expectation of an event is how many times, not the probability, it's how many times you expect a certain event to be the outcome. Like if I tossed a coin 10 times, I'll expect to get tails 5 times, and I'll expect to get heads 5 times, if it's a fair coin. It doesn't mean it's not a fair coin if it doesn't happen. If we get 4 tails and 6 heads, it doesn't mean the coin's dodgy. It's probability. It's not a this will happen. It's a expectation is what you'd expect compared to the probability. If I did it 1,000 times and you got 400 times I got heads and 600 times I got tails, that's when I'll start to go, maybe not a fair coin. But we're not dealing with biased stuff here. We're just talking simplistic probability. Firstly, experimental probability is just the probability that's listing what actually happened. Okay? As the formula says, experimental probability is the number of times the result occurred, whatever result we're discussing, the number of times the experiment was performed. So if I say what's the experimental probability on that coin I was talking about, what's the experimental probability of getting a head? Well, if I did it 10 times and got heads 4 times, well, the experimental probability is 4/10. Again, it wouldn't matter if you express it as 4/10 or 2/5, they're the same fraction. If you call it 0.4 or 40%, again, these are all totally good ways of expressing probability. You don't have to simplify the fraction. It often will be, but it's not a have to, no. Okay, so experimental probability is just saying really what happened. Alright? What else have we got down here? Experimental probability is also referred to as relative frequency. Like if something says, this event has a relative frequency of 0.4, that means when we perform the experiment, 0.4 of the time this thing we're discussing happened, 0.6 of the time it didn't. We normally just call it experimental probability, but if we refer ever to relative frequency, it's just saying how frequently it happened compared to the other events. Okay, suppose we tossed a coin 10 times and got the results. Okay, here we've got 7 heads and 3 tails, so we know that we've got 7/10 experimental probability of a head and 3/10 of a tail. Great. Okay, looks like I've typed this up before. Okay, so I've already said that content there. So here's an example. We've got the score on the die, 1, 2, 3, 4, 5 or 6, and the frequency, in other words, the number of times it occurred. Now, all these frequencies must add up to 60 because it says I rolled a die 60 times, and yes, here's the outcomes for all 60 times. I got a 1 12 times, I got a 2 8 times, and so on. Now, that's not the relative frequency, that's just the frequency. Okay, the relative frequency would be same as, again, the experimental probability. Let's just answer the first one. Find the experimental probability of rolling a 6. Well, a 6 happened only 5 times. So 5 out of the 60 times. Again, call it 1 in 12 if you want. That's also the relative frequency. What was the relative frequency of rolling a 6? 5 out of 60. Yeah, same thing. Find the experimental probability of rolling less than a 4. Well, less than a 4 doesn't include 4. Less than a 4 is rolling a 1, 2 or 3, which happened 12 plus 8 plus 9 times. So that's 29 times out of the 60 that happened. Probability of rolling an odd number is getting a 1, a 3 or a 5. They're the odd numbers. 2, 4 and 6 are the evens. So it'd be 12 plus 9, which is 21, plus 11, which is 32. Okay. Pretty nice stuff. And now we get to expectation. If you rolled the die 100 times, how many times do you expect to roll a 4? Now, normally when we get to theoretical probability, we're just going to say it's a fair die, and we'll say, look, if I roll a die 100 times, we're going to just times it by the probability, which in that case would be a sixth. You would expect a fair die to give me a 1 a sixth of the time, a 2 a sixth of the time, a 3 a sixth of the time, and so on. But here we're going to use the experimental probability. Okay, so the experimental chance of rolling a 4, as it says here, well, what did I get when I did it? It happened 15 times, so 15 out of 60 times I got a 4. So 15 out of 60 is a probability. You can also call that a quarter. And so if I rolled a die 100 times and a quarter of the outcomes I'm expecting to be a 4, well, what's a quarter times 100? 25 times. That's how many times I'd expect. There's a formula you can do there, and that's the expectation is equal to n times p. So that's the expected outcome is the number of times you do it times the probability of it occurring, be it an experimental question or a theoretical question. But let's see, does that make sense? If I do something 100 times and the probability of a certain outcome is a quarter, hopefully it makes sense that a quarter of the outcomes will be what we're discussing. And so yeah, I multiply it. A quarter of 100 be 25. I will get the, oh no, don't go on to that next, I think it's on the next page, don't it? The next one soon. Okay, theoretical probability is where we don't have experimental data about it. We just assume it's a, or we get told hopefully it's a fair die, it's a fair coin, and we know that if there's 2 outcomes, well, the probability of each one is a half. If there's 3 outcomes, the probability of each one is a third. Okay, so that's if they're fair and evenly distributed. Let's look at a few examples. Firstly, we've got to check our terminology. Between set terminology, which was our week 4 content, and probability terminology, which is this week's content. So, the sample space I referred to before, yeah, that's a universal set for an experiment. The sample space is just listing all the outcomes. If I'm tossing a coin, I said my sample space was head, comma, tail. That was also referred to as a universal set last week, if we're talking about the outcomes of tossing a coin. Yep. Outcome was each one of these things. A heads is an outcome and tails is an outcome. Last week we called them elements of the universal set. An event, well, is, it doesn't mean just one event. It could be an event of, like we said before, getting an odd number. So it might have a few elements in it, but an event has got to be a subset of the universal set. So if I did say, look, we're talking about rolling a die, 1, 2, 3, 4, 5, 6. Yes, I could define an event as evens. And the elements of evens is 2, 4, 6. And 2, 4, 6 is both an event that we've defined, and a subset of the universal set. 246 must be contained in the universal set. We don't get anything that's not within the universal set. Mutual exclusive events which have nothing in common. If one event happens, the other cannot. We talked about this last week in a Venn diagram. We drew a quick picture of something like this. That was A and that was B. That was what we referred to last week as disjoint, because there was no overlap. A and B can't happen. It's like the events of getting an even number and an odd number. There's no overlap, is there? I will draw them as two separate circles because the number can't be even and odd. You're even or you're odd. And here we call them mutually exclusive. Same thing, mutually exclusive or disjoint sets. A complementary event just means it's not A. Like the complementary event of evens is odds. Last week we said the complementary set of evens would be odds. Okay, complementary is the same thing. And we just use that dash notation. A or B, we used that last week. We just called it the union between two sets. Again, let's do it in terms of a Venn diagram. Last week we said, here's A, here's B, and the union is anyone that's in A or B or both. We said we're always going to use the inclusive or, which includes and. So we already defined A or B last week, and it's the same as union. A and B is just the bit in the middle. That's A and B, which last week we defined as the intersection. And independent events, it's easy to confuse that with mutually exclusive because they sort of sound the same. Mutually exclusive, we said, look, they both just cannot happen. Independent events is whether one event occurring is not influenced by whether or not the other event occurs. So say I'm tossing a coin 10 times in a row. Yes, heads and tails are mutually exclusive events, but if I'm talking about independent events, that's not like me saying, look, I tossed a coin, I got a head. Now I've got the coin in my hand again. Does the fact I just got a head influence the outcome of the next toss? It doesn't. It doesn't matter. I could have gotten 10 heads in a row, and I go to pick up the coin and toss it for the 11th time, and sometimes people think, well, it's really unlikely I'll get a tail. But let's look at this one single event. If I have a coin in my hand and I'm about to toss it, if it's a fair coin, that's 50-50. It doesn't matter what's happened before. It's just 50-50. Every time I pick up a coin that's fair and toss it, then it's 50-50. So that's an independent event. The tossing of a coin, each toss is independent because they don't affect each other. Okay, next, consider the experiment of rolling a die. The sample space is, S equals 1, 2, 3, 4, 5, 6. That's just listing it. He's using last week's notation. One of the possible outcomes is 5. So 5 is an element of the sample space. You bet. An example of an event is that you roll an odd number. There's an event, and it's listed as 135, and that's saying that 135 is a subset of the initial sample space. Agreed? Rolling an odd number and rolling a 6 are mutually exclusive. Okay, expressing that in set notation, rolling an odd number is the set 135. Rolling a 6 is a set of just getting a 6. The intersection sign was and. Remember, talking about them both happening, that happening and that happening. And what is the intersection? If you've got a 135 there and a 6 there, the intersection is nothing. Empty set. Remember, that was when we either wrote two sets of curly brackets or we just wrote this empty set. Complementary event, well, if A is 135, then A dash is 246, the exact opposite. Everything else that's in the sample space, or the universal set, that's not listed in that event, is the opposite of the event. The event that you roll an odd number or a 6, well, or is union. Okay, there's our union symbol. Odd number is 135, 6 is that. Union means, I don't care whether you're on that team or both, bring them all together. So 1356. The event that you roll a number which is odd and less than 4, well, odd ones are 1, 3 and 5. Less than 4 outcomes are 1, 2 and 3. And it says and again, we're back to intersection. What numbers are in both 1, 3, 5 and 1, 2, 3? 1 and 3 are. Okay, so we're still treading on the toes of last week a lot. if you roll, here's the example I did before, except I dropped coins. If you roll the die twice, the outcome of the first roll has no effect on the outcome of the second roll because they are independent events. Okay, when we get back to cards, there'll be questions that say, like, look, here's a set of cards. What's the probability of me picking out the Ace of Hearts? And look, it's 1 in 52. If I then put that card back in, what's the probability of picking out the Ace of Hearts again? Or any card I might pick, Ace of Spades, 1 in 52. The outcome of the first selection didn't affect the second one because I put it back in. I was walking up to the same full set of cards and picking a card out. But what if I changed the question and said, what's the chance of picking out the Ace of Hearts? Okay, 1 in 52. But you don't replace it. Did that outcome affect the second question? You bet. Because the first probability was a 1 in 52. The second probability, so that's from the first selection. The second selection, if I ask what's the probability of pulling out the Ace of Spades, well, there's still only one Ace of Spades in the pack, but there's only 51 cards left there now. Okay, so that's sometimes things are dependent, sometimes things are independent. How are we going to know? Just through the wording of the question. Did I replace the card and give ourselves the exact same scenario again? Or if I left it out, then things changed. Okay. Equally likely outcomes. Okay, well, an example, is say when I toss or roll a die. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Here's me jumping ahead a bit to tree diagrams. I just find them useful to visualise. There's a list of all the outcomes that could happen when I roll a die. Now, if it's a fair dice, we consider them to be equally likely outcomes. Okay? In theoretical probability, I don't have data on it, so I just assume that every outcome is equally as likely. Now, all of the probabilities have to add up to 1, because I've got to get one of these outcomes. So here it says, well, if you've got 6 individual outcomes, they're equally likely. The number of elements in the sample space, which is what this terminology means, well, there's 6 elements in the sample space. So that's a 1 over a 6. So I've got a 1 in 6 chance of each thing happening. So hopefully again that's logical, that what happens when I add up all of those 1, 6, I get 1. And they're all equally likely. So 1 over the number of elements in the sample space is the probability of each event if they're equally likely. Same with heads and tails. I'm either going to get a head or a tail. There's only 2 elements in the sample space, so it's a 1 on 2 and a 1 on 2. Okay, it's always got to add up to a half. If they're equally likely, they'll have the same probability on each arm. So, alright, we've already talked about it doesn't matter whether we're talking percentage, fraction or decimal. We've already talked about a certain event has a probability of 1 and the impossible event has a 0. So here it's saying the probability of getting an event that's in the sample space is 1. Well, okay, because any of that can happen, you're going to get one of them. This says the probability of getting an empty set is 0. Well, if you're doing something, you're going to get an outcome, like rolling the die. You're going to get a 1, 2, 3, 4, 5 or 6. One of them's going to happen. The probability of nothing happening is 0. Complementary events we refer to, that was with a dash. This concept here is just saying that, look, the complementary event, when added to the actual event, those 2 probabilities must add up to 1. If I tell you there's a 0.3 chance of event A happening, then I know that the event A dash will have a probability of 0.7. How did I know that? Because I know that they had to add up to number 1. So it's got to be one or the other. Event A probably happening, another way to say that is 3 in 10, hence there's 7 in 10 ways that A will not happen. And of course the probability of A happening plus the probability of A dash happening must equal 1. You can't have a list of probabilities adding up to anything but 1, okay, if you're listing all the events. So that's all this says. The probability of event happening plus the probability of its complement must equal 1. Or if we do a bit of algebra onto it, like what I've got here, if I say I'm going to leave that here and subtract PA from both sides, that tells us that P of A dash equals 1 minus P of A. So the probability of a complementary event happening is equal to 1 minus the probability of the original event happening. So it just helps us answer some questions quicker. Okay, not all. Let's look at this very simple example here. We've got a bag of jelly beans. Here's my bag of jelly beans in this example. Okay, what have we got? 5 yellow, 6 red, 7 green, 8 orange, and 9 black. Okay, how many jelly beans are in the bag in total? We've got 11 plus 7 is 18, plus 8 is 26, plus 9 is 35 in total. So what's the chance of getting yellow jelly bean? Well, there's 5 out of the overall 35. We don't add up just all the other things apart from the yellows. We say the probability of an event is the number of ways it can happen. Well, there's 5 ways I can pick out a yellow jelly bean. Out of the total sample space, the total number of things could happen. And that's 35 things could happen. There's 35 unique jelly beans. Some are the same colour, but there's 35 jelly beans. 5 out of 35, which can simplify to a 7. About orange, same concept. Well, we've got 8 orange out of 35, so it's 8 on 35. That just doesn't simplify. Probably a pink jelly bean. Good luck, there aren't any. It's 0 on 35, so it's just 0. Not black. Now here, I could either do it manually and say, well, that's the yellows plus reds plus greens plus oranges, or I could use complementary events and say, well, the probability of it being not black is 1 minus the probability of it being black. The probability of the jelly bean being black is 9 in 35. So the probability of it not being black, so it will B dash, will be 1 minus 9 on 35. The number 1 I know is 35 on 35. So that's 26 on 35. Okay. Or here we've just said, look, the probability it's not black is the number of jelly beans that are not black, which is 26 of them out of 35. Same thing. So you can see I've done it both ways here. Okay. And E, what's the chance of yellow or green? Well, or let's just look at, or in this case is going to be a plus. Why? Because which jelly beans satisfy the question, will it be yellow or green? There are 5 yellows and 7 greens. There are 12 jelly beans that satisfy that question. Now we said about or includes and, but there are no ands here. Okay, yellow or green, they're mutually exclusive events. Okay, there are no jelly beans that are yellow and green. So I don't have to get fancy, I'm just saying, look, there are 12 jelly beans that are either yellow or green, out of 35, and we're done. The last one says, what about neither yellow nor green? Okay, well now I know the probability of that they were yellow or green. F is the opposite of that. So I know the answer to F will be 1 minus the answer to E. 1 minus 12 on 35. So that's a 35 on 35 minus 12 on 35, which is 23 on 35. The other thing I could have done is said, well, there's 5 yellows and 7 greens, so I just want to add up the 6 reds, the 8 oranges, the 9 blues. They're the other things I could get. And of course, we still get 23 if you add them up. Okay, so 2 ways again to do it, which we have there. Now this is the formula I spoke of before, expectation. The probability, or the expectation of an event is talking about not the probability but the number of outcomes I expect to happen. I'm not promising it'll happen, but the most likely number of outcomes I expect. Well, it's equal to the number of times you do the experiment times the probability of it happening. So let's look. In 500 trials of throwing 1 die, what's the expected number of times you will roll of 6? Well, if I do something 500 times and I expect the probability of a 6, well, that's the same as the probability of a 1 or 2 or 3 or 4 or 5 or 6. It's a 6. 500 times a 6 equals 83 and a third. But don't report that. Can I throw a die 500 times and get 83 and a third 6s? No. What's the closest whole number to 83 and a third? 83. That's the expected number. My most likely outcome is getting 83 6s. The second most likely outcome would be 84. That's the whole number that's closest, that's second closest to 83 and a third. 83 would be first, 84 would be second. Now the next one is similar. In 75 spins of this spinner, what's the expected number of times it will land on red? Again, we're looking at it, we're seeing everything's fair, it's unbiased. Probably getting red is 1 outcome out of 4 outcomes. So I've got to do the number of times I spin it was 75 times a quarter, and that gives me 18.75. Again, the nearest whole number is 19. So what happens when we do 90 spins? If I do 90 spins of that spinner, and I know it's a quarter of the time I expect everything to happen, well, 90 times a quarter is 22.5. Now we know we've got to go to the nearest whole number, because I can't spin this spinner and get 22.5 times it landing on red. Mathematically, we would always round 22.5 up to 23, because that was the rule we used. We said, look, if this digit is followed by a 5 or greater, round it up. But that didn't mean to imply that 22.5 is closer to 23 than it is to 22. The truth is, 22.5 is a half away from 23, and it's a half away from 22. It's exactly slap bang in the middle. So real life doesn't know our rules about when we're going to round or not. So what's the answer in real life? They're both 22 and 23 are just as likely. If the probability calculation works out to be slap bang in the middle, then the outcome we must quote. We're wrong to say 23. We're right to say the most likely outcome, the expected number of times we'll get a 6 here, or sorry, a spin on red, is 22 or 23. So if you can round up or down because it's only a third or it's 0.75 and you're actually closer to the whole number, do that. But if you're right on halfway, then both events are equally as likely. Okay, so really this is felt like a nicer or a shorter week than last week. We've got some experimental probability, some theoretical, complementary expectation. Okay, I hope that's made sense, and please, get in touch if not. Alright, thanks a lot.